In this structural engineering made simple series, I will talk about an approximate method for frame lateral load analysis. It is called the portal method. Please take a moment and read the disclaimer at the bottom of this slide before we start. The portal method is an approximate solution for computing the bending moment, shear, and axial loads in beams and columns of a frame under a lateral load system. The method works best under ideal conditions as explained later. It is a convenient method for analyzing frames subject to wind or earthquake loads as a means of quick computation either for a preliminary analysis or for verifying the output from more advanced computer analysis. Basic assumptions. 1. The method works best in symmetric frames with equal beam span length and column heights. The level of approximation increases in frames with unequal beam span length and column heights. The point of inflection is at the mid-span of each beam and mid-height of each column. Lateral loads apply as point loads at each level. 4. Each interior column takes twice as much shear force than do the exterior columns. 5. Columns have the same cross-sectional properties and beams have the same cross-sectional properties as well. The next slide shows an idealized frame for use of the portal method with points of inflection marked at the mid-span of beams and mid-height of columns. It is also mentioned that there are variations of this method for conditions that are beyond those listed in this video as basic assumptions. The method presented in this video assumes the equivalent lateral loads have already been computed. They are labeled as P1, P2, etc. in the next slides. Separate analyses following an applicable code will need to be performed to determine these lateral loads based on the building location, its importance, and other conditions as pertain to wind and earthquake effects. Here is a frame with the points of inflection shown. The applied floor are P1 at the upper level in this 3-story frame, P2 at the mid-level, and P3 at the lower level or level 1. We start by making horizontal sections across the frame and write equations of equilibrium. We start from the top, making a section right above the column inflection points, and distribute the shear forces to columns. Recall that the middle column receives twice as much shear force than do the exterior columns. This is because the entire frame is assumed made up of portal units, as shown in the following figure. You notice that we get 2V in the interior column, and the axial load in the interior column is equal to 0. We have made a section right above the point of inflections of the upper level columns. The shear force is P1, which is now distributed to 25% each to the exterior columns and 50% to the interior column. Moving down to the middle level, the total shear is now P1 plus P2. If you look at the lower column, we have 25% of this total shear, each at the exterior columns, and 50% at the interior column. Going further down to level 1, the total shear now is P1 plus P2 plus P3. Again, 25% of that each goes to exterior columns, 50% to the interior columns. Finally, this one shows the shear forces at the lower half of the columns in level 1. Now, going back again to the upper level, notice that we can write all the internal forces through equations of equilibrium. The axial load in the column is N1, the axial load in the beam is N2, and the shear in the beam is V1. Knowing that the moments at the inflection points are equal to 0, we can now find all internal forces. The moment at the left corner is M1, which is 0.25 P1 H over 2. That is by multiplying the shear force of the column by 1/2 of the column height. Dividing this moment by the half of the span length of the beam, we get the shear force V1, which is 0.25 P1 times H over L. From equilibrium, the axial load in the exterior column, N1, is the same as the shear force V1, which is 0.25 P1 times H over L. And finally, the axial load in the beam is N2, which is P1 minus 0.25 P1, and is equal to 0.75 P1. We continue writing equations of equilibrium for the rest of the upper portion of the frame and find all internal forces. We can also draw the bending moment diagram. Here are all the internal forces in the upper portion of this frame. You notice that the axial load in the middle column is 0. However, the axial load in the beam starts at, as you can see, 0.75 P1. As you go to the right, it is further reduced to 0.25 P1. And the shear forces are shown. Notice that the axial load in the left column is 0.25 P1 H over L, and the right column is in the opposite direction, but with the same value. And here is the bending moment diagram with M1, as we said, equal to 0.25 P1 H over 2. You notice that the middle column does not receive any bending moment because it is a perfect symmetric frame. The next steps involve repeating the same procedure for the middle and the lower levels of the frame. For each level, we find the internal forces and draw the bending moment diagram. These steps are shown for the middle level of the frame in the next slides. See if you can write the same equations for the lower level as well. Here are all the internal forces at the middle level. Again, realize that the axial load in the middle column is 0. And the corresponding bending moment diagram. M1 already computed. M2 is computed similarly. Is the shear force times the half of the height of the column. M2 is equal to 0.25 P1 plus P2 times H over 2. And M3 is the moment in the beam, and that is found by simply writing the equilibrium of the moments in that left joint. In other words, M3 is equal to M2 plus M1. As we said, similarly, we can compute internal forces and draw the bending moment diagram for the entire frame. At this point, we put some numerical values for the frame. We use L of 18 feet, H of 12 feet, and P1, P2, P3 each equal to 5,000 pounds. Using the equations given, the three moments M1, M2, M3 each is equal to 7,500, 15,000, and 22,500 foot-pounds respectively. Furthermore, the bending moment for the exterior column of the lower level is M4, which is 0.25 times the total shear at that level. The total shear is P1 plus P2 plus P3 times half of the height of the column. So we'll have 22,500 foot-pounds. And finally, the bending moment for the beam in the lower level is obtained from equilibrium, which is the summation of m power n 2, m4 and m2, and that is 37,500 pounds. With these values, the entire bending moment diagram for the frame is now plotted. Here it is. The values are listed at the bottom. Notice that the middle column is not subject to any bending moment, as we explained before. This is because of the frame being completely symmetric. It is again emphasized that this is an approximate method for frame analysis, under lateral loading only. As the geometry of the frame changes, and if the beam span length and column heights are not equal, the level of accuracy of this method decreases. Thank you for watching this video.